All right, welcome back, everyone. Calling all engineering students and focused learners, welcome to today's Explainer. Today, we're doing something I absolutely love. We are bridging that notoriously tricky gap between theoretical digital signal processing concepts and hands-on, highly practical engineering applications. So we aren't just going to stare at math equations on a whiteboard today. No way. We're rolling up our sleeves and diving directly into Python code to clean up some seriously messy, corrupted real-world signals. We actually have 3 really interesting major engineering challenges lined up for us today. First, we're going to clean up a vital medical signal. Then we'll try to silence some aggressive interference coming straight from an electrical grid. And finally, we're going to repair some corrupted visual data. Now, for each of these 3 case studies, we're going to use the exact same structured framework. We'll define the problem, we'll break down the Python logic line by line, and then, the best part, we'll reveal exactly how that mathematical filter translates into a beautifully clean visual output plot. By the end of this explainer, you are absolutely going to have a robust, working understanding of how to deploy these essential DSP algorithms yourself.
Here is a quick look at our roadmap for today's session. Number 1, welcome to DSP Lab. Number 2, ECG baseline wander removal. Number 3, power line hum removal. Number 4, image denoising fundamentals. And finally, number 5, real-world DSP challenges. Let's just jump right in.
Section 2. ECG baseline wander removal, filtering medical artifacts.
Okay, let's tackle our first challenge. And honestly, this is a perfect way to build your filtering foundations. We are looking at filtering out medical artifacts from a vital, non-invasive diagnostic signal. But to solve any problem, we first have to deeply understand it, right? So, an electrocardiogram, or ECG, measures the electrical activity of your heart. In a textbook, it looks perfect. But in a clinical setting, when you attach electrodes to a living, breathing human being, things get incredibly messy. If a patient so much as takes a deep breath, shifts their weight on the bed, or if the electrode contact just isn't perfectly flush with the skin, it creates this frustrating phenomenon we call baseline wander. Basically, this is a very slow, low-frequency noise, usually hovering around 0.1 to 0.5 hertz. So instead of your heartbeat plotting nicely along a flat, stable zero-voltage line, the entire signal slowly drifts up and down. It's like the heartbeat is riding on top of a slow ocean wave. And this drift is a massive problem because it completely obscures the essential P, QRS, and T waves. If those are hidden, automated systems fail and doctors simply cannot analyze the patient's cardiac health properly.
So how do we fix it? Well, we're going to build a solid 4-step Python pipeline. First, we'll define our parameters and simulate both that pristine clean heart rate and our baseline wander noise. Second, we're going to design an infinite impulse response, or IIR, Butterworth high-pass filter. Third, we'll apply zero-phase filtering, which, as you'll see, is a completely non-negotiable technique when you're handling biomedical data. And fourth, we'll use matplotlib to generate our visual plots and actually prove that our filter did its job.
Let's break down this first chunk of code together. Looking at step 1, we're utilizing the NeuroKit library to simulate a pristine 10-second ECG signal, and we're sampling it at 1,000 Hz. That is our clean variable. But like we just talked about, real life isn't clean. So we need to intentionally generate a 0.2 Hz sine wave to represent that slow, drifting baseline noise. We then just add those two together to create our noisy_ECG signal. Now let's move to step 2. This is where the actual engineering happens. Check out how we define our cutoff frequency. We're setting it to 0.5 Hz. Why exactly 0.5? Well, think about it. It sits perfectly in the sweet spot between our 0.2 Hz noise and the roughly 1 Hz minimum frequency of a resting human heartbeat. Next, we set our filter order to 4. This is a deliberate design choice to balance getting a nice sharp cutoff without causing the signal to aggressively ring or distort. Then, we take that 0.5 cutoff frequency and normalize it against the Nyquist frequency. If you remember, Nyquist is always half of our sampling rate, so in this case, 500 Hz. Finally, we pass all those parameters into our Butterworth function to mathematically generate our filter coefficients.
Moving further down the script, we hit step 3. And I really want you to pay attention here, because this is absolutely crucial. Look at line 30, where we apply the filtfilt function for zero-phase filtering. Notice that we don't just use your standard everyday filter function. Why? Well, when you run a raw signal through a standard IIR filter, the mathematics naturally introduce something called a phase delay. This physically shifts the signal forward in time. Now, think about what that means in a medical setting. Shifting the exact timing of a heartbeat is totally unacceptable. It could lead to a false diagnosis of an arrhythmia. The zero-phase filter, filtfilt, completely solves this. It filters the data forward, then it reverses the array and filters it backward.
Those phase delays effectively cancel each other out, leaving you with exactly 0 time distortion. After we lock that in, we jump to step 4, where we're simply using matplotlib to generate 3 stacked subplots, so we can visualize our clean components, our noisy combination, and of course, our final filtered output.
And boom, here is the reveal. This brilliantly illustrates the fruits of our labor. Let's map this out. Starting right at the top panel, that solid blue line represents the clean, high-frequency heartbeat we want. The dashed orange line, that is that slow, rolling 0.2 Hz baseline wander. Now move your eyes to the middle panel. This is our corrupted signal. Notice how the sharp, distinct peaks of the heartbeats are literally being dragged up and down by that massive drift. The whole signal is totally off-center. It's a mess. But finally, look at the green panel at the bottom. This is our output right after applying that high-pass filter. It's beautiful, isn't it? The low-frequency drift has been surgically flattened to 0, and, crucially, because we used a cutoff of 0.5 Hz combined with zero-phase filtering, the high-frequency QRS peaks of the heartbeat remain perfectly intact. They aren't distorted, and they are perfectly aligned in time with the original signal. We successfully restored a stable, highly accurate baseline.
Section 3. Power line hum removal. Silencing AC electrical interference. Okay, that was a fantastic start with the ECG signal. But now we're going to completely shift gears. Let's move from dealing with slow rolling artifacts to incredibly fast, aggressive electrical interference. Here's the reality. Every single electronic device, every cable, every sensor you use out in the field essentially acts as an antenna. And what do you think it picks up? It picks up the massive electromagnetic field generated by the AC electrical grid humming in the walls all around you. Depending on what country you live in, this interference creates a constant, relentless hum at exactly 50 Hz or 60 Hz. Now, unlike the baseline wander we just looked at, which was spread out over very low frequencies, power line hum is intensely, stubbornly concentrated at one single, very specific frequency. If you don't aggressively address it, this pure sine wave will completely overwhelm and drown out smaller, more subtle signals.
Let's look at the Python setup for this specific scenario. First, we set our sampling frequency to 200 Hz. Our clean signal of interest, the data we actually want to keep, is a low-frequency 5 Hz sine wave, and we give it a standard amplitude of 1.0. But then, look at how we generate the hum noise at 50 Hz. Check out the code where we set the hum amplitude to 2.5. Think about that for a second. We are deliberately making the noise 2.5 times stronger than our actual signal. Why? Because this is exactly what happens in the real world when a tiny, unshielded sensor wire runs a little too close to a main power line. We add those two arrays together to create our noisy signal, and as you can imagine, our poor 5 Hz signal is now completely buried alive.
So notice how our mathematical approach has to change here. A high-pass or low-pass filter simply isn't going to cut it for this. Instead, we use what's called an IIR notch filter. A notch filter is basically a band stop filter, but with an incredibly narrow stop band. Just like before, we normalize our target 50 Hz frequency against the Nyquist limit, but then we pass in a new variable called Q, which stands for quality factor, and we set it to 10. A high Q value is what ensures our notch is deep, sharp, and highly precise. We calculate those filter coefficients, and once again, we strictly use our zero-phase filtering trick to guarantee we don't introduce any temporal distortion. Then, moving further down the script, we define a custom calculation function to plot our frequency spectrum. This uses a fast Fourier transform, or FFT, to convert our time domain signal into the frequency domain. It takes the absolute magnitude, normalizes it, and then cleverly slices only the first half of the array. We do that because the Fourier transform outputs a mirrored spectrum, and we literally only care about the positive frequencies for our plot.
Before we look at the visual results, let's just quickly clarify why you, as an engineer, must always choose the right tool for the exact noise profile you're facing. Think of a high-pass filter like a massive dam. It blocks a whole ocean of frequencies below a certain threshold. That made it absolutely perfect for the widespread, slow drift of our ECG signal. But a notch filter? A notch filter acts like a sniper rifle. It surgically targets and removes one highly specific frequency, in our case that annoying 50 Hz AC hum, while leaving the 49 Hz and the 51 Hz frequencies sitting right next to it virtually untouched.
All right, let's look at the dramatic impact of that notch filter in action. Over in the time domain plot on the top left, the noisy signal is just this chaotic, high-frequency mess. It's completely obscuring the dashed blue clean signal hiding underneath it. You can't see the 5 Hz wave at all. But if we shift our focus to examine the frequency spectrum on the top right, the root of the problem becomes blatantly obvious. Look at that absolute skyscraper of a peak sitting exactly at 50 Hz.
It's completely dwarfing our tiny 5 Hz signal on the left. Now, observe the post-filter spectrum down at the bottom right. That 50 Hz skyscraper, it has been entirely vaporized. There is nothing with a tiny, almost imperceptible notch left in its place. And as a direct result of that precision strike, check out the filtered time domain plot on the bottom left. Our solid blue line now perfectly, flawlessly tracks the dashed orange original signal. The 50 Hz electrical interference is totally gone, and thanks to our zero-phase filtering, there is absolutely zero temporal distortion. It's a perfect cleanup.
Section 4. Image Denoising Fundamentals. Cleaning up visual data.
So far today, we've only dealt with one-dimensional time series signals. Now let's level things up and transition to a two-dimensional matrix. Visual data is a whole different beast, and it suffers from entirely different forms of interference. One classic example you'll run into is salt and pepper noise. This usually happens during analog to digital conversion errors, or maybe you have dead pixels on a camera sensor. It's a type of high-frequency visual static. It's characterized by random isolated pixels suddenly being forced to extreme maximum intensity, which visually looks like white grains of salt scattered around, or extreme minimum intensity, which looks like black flakes of pepper. Now, because this is inherently high-frequency noise, we actually need to flip our previous filtering logic totally on its head.
To demonstrate how to solve this, we are actually going to synthesize an image of the Bangladesh flag right from scratch. In step 1, we set up an image matrix. We make it 300 pixels high by 500 pixels wide. Then we set our noise probability to 10%. That means, on average, 1 in every 10 pixels is going to be corrupted by our salt and pepper static. We also define a filter sigma value of 2.8. You can think of sigma as the master strength dial for the blur we're going to apply later. Then in step 2, we actually paint the flag. We create a solid background field of dark green using an unsigned 8-bit integer array. To get at the red circle, we just use some simple geometry, specifically the squared distance formula, to calculate every single pixel that falls within a specific radius from our exact center coordinates. Once we find them, we mask those specific pixels and turn them a bold crimson red. Okay, we have our perfect flag. Now let's completely mess it up. In step 3, we generate a grid of random coordinates, and we use our numpy.randomChoice function to randomly assign extreme values, either completely black or completely white, across all 3 RGB color channels. This successfully peppers our pristine flag with that harsh static. Then, step 4 is our solution, a Gaussian filter. First, we have to cast the noisy image to a floating point array, just so the algorithm can perform accurate decimal math. Then we apply the Gaussian filter using our sigma value of 2.8. But look incredibly closely at that sigma array in the code. We pass the 2.8 parameter in for the x-axis and the y-axis, but we put a hard 0 for the final parameter. That 0 at the end is absolutely vital. Why? Because it tells the algorithm to smooth the image across the spatial height and width, but not across the color depth channels. If you blurred the color channels together, our nice red and green flag would turn into a muddy brown mess. Ultimately, this Gaussian filter is acting as a 2D low-pass filter. It mathematically averages the intensity of each individual pixel with its surrounding neighbors, completely washing out those isolated extreme salt and pepper spikes.
Let's look at the final visual comparison here to see how we did. On the left side, we have our noisy import flag. As we programmed, 10% of the pixels are corrupted, creating a really harsh, high-frequency static overlaying the clean geometry of the flag. Now look on the right. There is our filtered output. The algorithm was incredibly successful at averaging out that black and white noise, restoring the deep green and crimson red fields beautifully. But there is a catch. Look closely at the edge of the circle. This brilliantly illustrates a core, fundamental trade-off in digital signal processing. Remember, a low-pass filter suppresses high frequencies. Well, a perfectly sharp edge in an image, like the boundary between the red circle and the green background, is technically composed of high-frequency spatial data. So, because we aggressively filtered the high-frequency static noise, we also accidentally blurred the sharp edges of our circle. In the world of DSP, you are constantly playing this balancing game. You are balancing noise suppression against the preservation of sharp, transient features.
Section 5. Real-world DSP challenges. Where will you apply this next?
Well, we've covered a tremendous amount of ground today, but honestly, this is just the beginning of your journey. The tools you've seen today, the high-pass, the notch, and the low-pass filters, these are the absolute foundational building blocks of all modern digital infrastructure. Before we wrap up, I want to leave you with a provocative thought to help with your post-laboratory problems. Imagine you are working on restoring a vintage vinyl audio recording, maybe a classic Beatles record, but it's filled with random, high-amplitude clicks and pops from dust on the needle. Conceptually, this is essentially the exact audio equivalent of the salt and pepper image noise we just looked at. But here's the major catch. If you just aggressively apply a standard linear low-pass filter to the audio track, you will completely muffle the music. You'll destroy the crisp hi-hats, the bright vocals, the sharp snare hits. The linear tools we use today wouldn't work perfectly for this. So, I want you to think, what type of non-linear filter could intelligently detect and suppress just those isolated microsecond pops and clicks without touching the surrounding musical masterpiece? Figuring that out, well, that is the real art of digital signal processing. I'll leave you to ponder that challenge. Keep experimenting, keep writing that Python code, and I will see you in the next explainer.